Question 25 from the homework is a pretty challenging question, and it's because there are three different calculations we have to do to answer question 25. So basic information, right? We're given 110 grams, 110.1 grams of a substance, and it has a molar mass of 189.5 grams per mole. And we take that substance and we cool it down from 233 degrees Celsius. We're going to cool it down to 160, which is the boiling point. 160.3 degrees Celsius is my boiling point. After I cool it down, I'm going to then go through a phase change, right? So I'm a gas here, go through my phase change, and then I'm going to cool it down the rest of the way from 160.3 degrees all the way down to 147.6 degrees Celsius. So you might think it's just one calculation to calculate from 233 to 147, but it happens to encompass the boiling point. That means we go through a phase change, and that's a separate calculation. So three different calculations we're going to have to do within this calculation. The first one, and I should identify that, right, we're dealing with the liquid phase here. So for the first calculation, we're going to have to use Q equals MC delta T. And we're going to have to use the specific heat of the gas because we're dealing with the gas phase. That's our first calculation. And our third calculation is going to be a variation of that. Our third calculation is also going to be Q equals MC delta T, with the exception of now we're dealing with the liquid phase. And so I'm going to use the specific heat, right, of the liquid phase. And then our middle calculation, and that's from there to there. Our middle calculation, we're going through a phase change. And so for that, we need Q equals N. And here we're going from a gas to a liquid. That's our vaporization or heat of vaporization. So delta H, my vaporization, that is our second calculation. So three separate calculations we're going to have to do for each of those steps of this process. So they give us a little more information, right? They tell us that the heat capacity of the liquid, so is 1.62 joules gram degrees Celsius, and then of the gas is 104 1.04 joules gram degrees Celsius. And my heat of vaporization, and just be careful because if we look at the units in heat of vaporization, 78.11 kilojoules per mole. The first two are based on mass. The next one is based on moles of energy. So we've got a little bit more work to do for the second calculation. So calculation one, Q equals MC delta T. So Q equals my mass, 110.1 grams. My specific heat of the heat capacity of the gas is 1.04 joules gram times degrees Celsius. And my delta T is final minus initial. So when you're finding delta T, right, it's always temperature final minus temperature initial. So initial is 233. So 160.3 minus 233, it's a negative temperature. And that makes sense because if we go from a gas and we cool something down, right, when we cool anything down, we're releasing energy. So we should have a negative value of Q. So if we take a look at that temperature change, right, our temperature change is about 72.7 degrees Celsius. For our second calculation, Q equals N. N is our number of moles. So first we should find moles, right? And we know moles equals grams over molar mass. So moles equals, I have 110.1 grams. My molar mass is 189.5 grams per mole, right? So I divide and I'm going to get like 0.58 moles. .581 moles, and then my heat of vaporization, right? Q equals my number of moles, 0.581 times my heat of vaporization. And vaporization would be endothermic, right? Going from a liquid to a gas is endothermic. We're going from a gas to a liquid. That's going to be exothermic. We're going to release energy. So negative 78.11 kJ per mole. So multiply, and we get approximately 45.38 kilojoules of energy. And that's for step 2. Step 3, we're back to Q equals MC delta T. My mass is still 110 grams. I'm just no longer a gas. I'm in the liquid phase. And I want to use the heat capacity of the liquid, which is 1.62 joules gram times degrees Celsius. And my delta T for the last one, final, right, minus initial. So 147.6 minus 160.3. And I get a negative 12.7 degrees Celsius. So I need to multiply these together to get the total energy, right, for step 1 and step 2, sorry, step 3. So if I multiply 110 I get 8,324 joules. It's asking for the answer in kilojoules. So I know that for every 1,000 joules, I have 1 kilojoule. So I've got negative 8.32 kilojoules from step 1. Step 2 was negative 45 kilojoules. And then step 3, going to multiply 110 by 1.62 by negative 12.7, and I get about negative 2,265 joules. And again, they're asking for the answer in kilojoules. So I'm going to divide by 1,000 again to get that step 3 is approximately negative 2.27 kilojoules. And then part D, they're asking for the total energy, right? The total energy would be the sum of all of these energies. For cooling down the liquid, or the gas, we go through that phase change, going from a gas at 160 to a liquid at 160, and then we cool that liquid down further to reach 147 degrees Celsius. So the total is going to be, adding all those together, about 55.97 kilojoules of energy, right, in total would be released through all 3 of those steps. But that's the trick, is that each part of that diagram, each part of that curve requires a different calculation depending on, are we dealing with a liquid or a gas? Are we dealing with a phase change, right? Each of those calculations are a little bit different. So hopefully that helps with question 25. It really is a challenging question because of those aspects. And on part 2, right, they give you information in kilojoules per mole, whereas everything else was based on grams. So we had to go and find moles of this unknown compound. So there were a couple of tricks thrown in there, as well as the challenge of breaking that into 3 separate calculations.